So far with our integration, all we've been doing is finding area. Normally underneath the curve or maybe between two curves. Well, starting in 7-3, the way this particular book organizes it, we are going to start talking about volume. What we're actually going to do is take those areas you've been finding and we're going to revolve it around something. Either perhaps the x-axis, the y-axis, or maybe some other line. And maybe you could look at it as perhaps, this is obviously a solid, maybe here's your x-axis shooting through like that. Do you see how that has pretty much been revolved around that x-axis? And some people, you could think of it this way, you know, all those rectangles we've been talking about? It's basically that rectangle attached right here and just revolved down and around. And does it create a three-dimensional object if you take that two-dimensional object, the rectangle, and revolve it around the x-axis? It does. It kind of forms something that almost looks like a quarter. If you think about a quarter turned on its side, you can kind of see that there would be a possibility there. Yeah. Okay, the question there is the half circle, would it be parabolic? No, what we're basically doing is we're going to take a two-dimensional rectangle, and we're going to keep them rectangles, and we are going to revolve it. This is going to be completely straight right here. The reason I had to turn it a little bit is so that you could see the disc. If I left it straight on like this, if I showed, hey, there's a disc, well, it would look like a rectangle. That's why I had to just turn it a little bit so you could see the back portion. Otherwise, you'd be like, what are you talking about? Okay. So basically, yeah, if I had a quarter, which actually I think I do. You're basically looking at it like this. If you cut it, just take this portion right out in the front, that's your rectangle, which you revolve around really the center of this quarter. And it becomes three-dimensional. Obviously, we could do it the other way. It could be this turns it and just makes it a y-axis. Obviously, these rectangles here are dx. This rectangle here would be, if you're going that way, dy. And that's why I had to introduce that dy problem in 7-2, so you've at least seen one that way. Well, then how come in this formula here, well, we see a pi, we see a big capital R, and we see a square. Well, the reason you see those in there is if I did ask you to find the volume of this, would you agree it's a cylinder if we talk about geometry terms? Yeah. And to find the volume in geometry, it's the area of the base times the height. Right? That's how we found cylinders. And how would we find the area of this? Well, we would take pi r squared. That's the area of the base, right? And we're going to say w for our height, and I'll explain why it's w a little bit later. Basically what that, well, I can tell you now. Basically, it's how wide the rectangle is going to be. That's why it's w. How wide is the rectangle? And the nice thing for us, how wide the rectangle is, I kind of had it drawn over there. How wide the rectangle is dx. I just had it drawn over there, right? That's how wide I called it. And basically, r is whatever the radius happens to be, you squared it. Does the pi have to be put out front? No, but it's a number. And so you can throw it out front if you wish. Well, for the height of it, what we're normally going to do for height is we're going to use whatever function we have. You're going to see it when we get to a graph. I think it'll be a lot easier when you see the first example to make the disk make sense. We're going to put more than one disk in. We're going to try and put in a ton of disks. Or in other words, we're going to find the limit of how many disks we can put in. The more disks you put in, the more accurate it'll be. Exactly, and that's what the limit process does for us. It basically gives us the answer. For example, you can see right there is basically your graph of the square root of sine. So why don't you go ahead and get that in there. It's 0, 0, obviously. This is pi over here. This is pi over 2. I know that because in the directions I told you to go from 0 to pi. And so that's the graph that we made. Obviously, this is 0 right here. Okay? And that is actually right up there at 1. Because let's face it, if you put pi over 2 in there, sine at pi over 2 is 1. You take the square root of that, it is 1. So no big surprise that that's where it ended up. Okay? And so that's about what the graph looks like, correct? And I'm revolving it about the x-axis. And what you're going to get used to doing, and what I do a lot of times, is I think we can agree that that's the x-axis right there, right? I put a little symbol in there like that to remind me where I'm revolving it. Because let's face it, you could get distracted for a minute or two and somebody's talking to you, and then you come back and you're like, oh, where was I revolving it about again? I forgot. Now, do you remember when we approximated these areas? We sat there and just threw a bunch of these in there, right? Was it perfect? No, normally we had the left-handed, the right-handed, and then basically we learned that if you do the fundamental theorem of calculus, you're just saying throw in as many rectangles as I can and add them up. Well, what we're doing is almost the same thing. But what we're really kind of going to end up doing is, yeah, really, there are a lot of rectangles that could be put in there. But what we're really doing is putting in a bunch of disks. Okay? Because this rectangle that I just had drawn right here, do you see how that could get revolved around and form a disk? Could this rectangle right here get revolved around and make a disk? Same thing as you go. Could I do more than 5? Yeah. Could I do 100? Yeah, I could go as far as, could I just do 2? Yeah, but we're going to do the problem in a way that it will help us out. Do you see the disks? That's the number one most important thing. Do you see them? We're not going to do the area underneath. We're going to do volume. Okay? We're changing the process into a volume process. Okay? But we're still using the rectangle so that you can see where the disk is coming from. It did, yeah, that's where the smartboard really wasn't cooperating very much on that one. So that did take some time, so I hope you appreciate that. Now, what we have to figure out, we are revolving around here. So do you agree this distance, well, in every instance right there, that distance is the radius of that disk? And how can I represent that? Well, basically, it's whatever the function is, right? In this case, it's the y value of the function, right? And so if we're going to go to this formula that says put pi out front and then go from A to B, and it's called capital R. The reason it's called capital R is you will be introduced to a lowercase r later. Okay, so that's why there is an uppercase R. Well, then really the biggest question once you see the disks is what is the radius? How do I figure it out? Does the radius change as I go throughout this problem a little bit? It does. It gets bigger, smaller, depending on where you are, right? But isn't it always whatever the y value is of the function at that particular spot for that particular rectangle? Yeah, left-handed, right-handed, it doesn't matter. It's just basically the y value. So what you can do in place of that is just put the function. So you may have seen the square root of sine of x as being a very mean thing for me to start you off with. But actually it was very nice because I have to square it. Exactly. This square has to come on down because to find volume, it's pi r squared times height. Okay. Now, how wide is each one? Well, each one is, it's a dx rectangle, right? So each one, the width is just dx. Pi is out here. Do you have to put pi out front? No. I do. Because I don't want to deal with it the whole time. From where to where? I erased it on purpose. 0 to pi. Yep. Now, as I mentioned earlier, the question was asked, are we going to be using calculators today? And I said no, because in my notes here, I have specified that we should do these by hand to refresh our memory. Now, before I would even integrate this one, I would do simple algebra first. What is something that's actually quite simple that I could do before I do anything? Yeah. Yeah. Really, do I have to sit here and deal with the square and the square root and all of that? No, they just naturally cancel each other, right? And let's face it, when squares and things like that showed up in integration, didn't it make them harder? So if we can get rid of them legally or algebraically, probably not a bad idea. So really all I'm trying to integrate is, yeah, sine of x. Is that something we know how to integrate? Do we need substitution, integration by parts, or anything like that for this one? No, it isn't just flat out. So here we go, pi is out front. I like to put brackets. I don't know why I do that, but it just makes me feel more comfortable when I have that pi out front, so I remember to distribute it. Well, the derivative of sine is cosine, so the antiderivative is negative cosine of x. Boy, it's been a long time since I've made you do fundamental theorem of calculus by hand. Again, I've shown you how to do it on the calculator. Let's see if you remember the notation. How do I basically show that I've taken the antiderivative here? Obviously, I didn't write the squiggle anymore. Nope. You just straighten out the line. To remind yourself that, hey, I took the antiderivative. Because again, could you get distracted, come back and be like, wait a minute, did I integrate? Did I not? I can't remember. Now, if you see that notation, you should know, yeah, I did. Okay. On this particular one, here's again what I would do. I would put the pi like this. That's this particular pi out front right there. That's the one I'm putting out front over here. Now put pi in. It says negative cosine of pi. Well, let's find pi. Where is that on our unit circle?
180.
Yeah, 180 basically. And so the ordered pair over here is negative 1 comma 0. And which of those two values is actually cosine? Negative 1. So this is basically a negative 1. So in other words, a positive 1, correct? Now remember, in the fundamental theorem of calculus, do you add what's on the bottom or do you subtract what's on the bottom? Yeah, you got to subtract whatever you get when you put 0 in. Well, where is 0 on that unit circle over there? Yeah, it's basically the very opposite side. And so it's 1 comma 0. And so it's basically 1 minus a negative 1, right? Because it's negative cosine of 0, right? And what some people would have done on this one is taken this negative and thrown it on the pi so they didn't have to have so many negatives in the problem. Do you see how you could do that? That's probably, again, if you have that choice, you might want to later. And so the answer is 2 pi.